Simple versus compound interest and discount rates. An interest rate represents the rate at which a deposit made today would appreciate in value over a certain term, where at the end of the term one would receive the initial deposit back plus the amount of appreciation. Interest rates can either be quoted as simple rates or compound rates. Simple rates. For a simple interest rate, we assume that the appreciation on the investment only applies to the original amount invested. In other words, if an investor were to invest 100 Rand in an account paying a simple rate of I per period, then after one period, the investor would have an investment worth 100 Rand initially invested, plus the interest earned on that initial 100 Rand investment. So, after one period, they would have 100 times by 1 plus I. If the investor chose to keep their investment in the account for another period, then after two periods, their investment would be worth the initial 100 Rand invested, plus the interest from the first period, which is equal to 100 times by I, plus the interest from the second period, which is also equal to 100 times by I, seeing as though for simple interest, one would only earn interest on the initial amount deposited. This leads to a final value of 100 multiplied by 1 plus 2I. One can generalize this to an investment made for n periods in the same account, where the value of the investment at the end of n periods would be 100 plus 100 multiplied by I multiplied by n, the number of periods. This is equal to 100 multiplied by 1 plus ni. And this is the general formula for simple interest rate calculations. Compound rates. For a compound interest rate, we assume that after an investment has appreciated at the end of a period, it earns interest on both the initial amount invested and additionally on the interest earned in previous periods. In other words, if an investor were to invest 100 Rand in an account paying a compound rate of I per period, then after one period the investor would have an investment worth 100 plus the interest earned on the initial 100 invested. In other words, 100 times by 1 plus I. If the investor chose to keep their investment in the account, then after two periods, their investment would be worth 100 times by 1 plus I plus 100 times by 1 plus I multiplied by I, seeing as though one would earn interest both on the initial amount invested, but also on interest earned from prior periods. Thus simplifying, after two periods, the investment would be worth 100 times by 1 plus I squared. One can generalize this to an investment made for n periods in the same account, where the value of the investment at the end of n periods would be 100 times by 1 plus I to the power of n. Compounding periods and conventions. Compound interest can be quoted in a number of ways depending on how often interest is paid or compounded to an investor. The table below summarizes a few interest rate conventions. I, for a rate compounded annually, that is just once per annum. This is also called the effective rate. I2, where this is the interest rate compounded semi-annually. In other words, interest is paid or compounded to an investor twice in the year. I4, where the rate is compounded quarterly, in other words, paid 4 times in the year. I12, where the rate is compounded monthly, in other words, the interest is credited to the investor every month. I52, the rate compounded weekly, where the interest accrues to the investor at the end of every week. And IN for a general number of compounding periods of n times per annum. For a rate compounded continuously, what we mean is the interest is paid so often into the investor's account that we just assume that it's paid every split second, if you wish. So for a rate compounded continuously, we would use Euler's number E and we would raise it to the power of the continuously compounded rate. So this is often used as an approximation for interest that's earned daily on an investment or any frequency greater than daily. In other words, every hour or every minute, a certain amount of interest is paid to the investor's account. And then you'd use the continuously compounded rate of interest for that. So if an interest rate is compounded n times per annum, the general convention is to annualize the rate by multiplying the interest rate earned in each nth part of the year by n, the number of times the rate is compounded during the year. And this is best illustrated by way of a few examples. Example 1. If an interest rate is 10% per annum effective, then each year the interest will only be paid once. In other words, compounded once per year. So at the end of 1 year, the interest received will effectively be 10%. If an interest rate, example 2, is 10% per annum compounded semi-annually, then interest will be paid every 6 months, in other words, twice a year. So we denote that by I2 is equal to 10%. And here we have that each 6 month period would pay interest of I2 divided by 2, or 5%. You'd receive 5% interest every half year. Example 3. If an interest rate is 10% per annum compounded monthly, then interest will be paid every month, that is, compounded 12 times per year. So we denote this by I12 equals to 10%, and each month you'd receive interest of a twelfth of the annualized rate of interest. So you'd receive interest of 0.833% per month if the annual rate of interest compounded monthly was 10%. Example 4, we can generalize this to n periods and denote this by in equals 10%. Now, each of these n periods would pay an interest rate of in divided by n percent. It should be noted that even if all of the interest rates above had the same annual quoted rate of 10% per annum, but if each had a different compounding frequency, the interest rate earned at the end of a year would be different for each of these investments. We can expand this in the examples to follow. So we need a formula that will standardize compounded rates so that they can be converted to annual rates and rates compounded at various other frequencies. This will easily enable us to compare different investments with one another. The following formula can be used when one wishes to convert between an interest rate compounded n times per annum and one compounded m times per annum. 1 plus in over n to the power of n is equal to 1 plus im over m to the power of m. We can simplify this to obtain in is equal to n multiplied by, open brackets, 1 plus im over m to the power of m over n, and we subtract 1 from that. Close brackets. We can illustrate this in the following examples. If an interest rate is 10% per annum compounded semi-annually, what is the equivalent annual effective rate? Here we wish to solve for the effective rate where n is equal to 1, and we're given a semi-annual rate, I2, equal to 10%. So therefore in our formula, m is equal to 2. We substitute the various values into our formula, and in practice we denote I1 by just I, and this gives us I is equal to 10.25%. In other words, the equivalent effective rate is 10.25%. Example 2. Convert 15% per annum, compounded quarterly, to its equivalent monthly yield. Here we wish to convert I4 to an equivalent I12 rate. Therefore, M is equal to 4 and N is equal to 12 in our formula. We substitute the various values into our formula and we arrive at 14.82%. So, in other words, a 15% per annum rate compounded quarterly is equivalent to a 14.82% rate compounded monthly. Continuously compounded interest. If we were to increase the compounding frequency to a large enough extent and assume an investor receives interest continuously throughout their investment, then a continuously compounded rate of interest would be used. In practice, continuously compounded rates of interest are used to approximate interest earned on investments when interest is paid daily. They are also a very important concept in the pricing of derivatives. Using the formula below, 1 plus in over n to the power of n is equal to 1 plus im over m to the power of m, we can set n equals to 1 and re-express the left-hand side of the equation as 1 plus I is equal to 1 plus im over m to the power of m. Then algebraically manipulate the right-hand side of the equation to yield 1 plus 1 over m over im, all of that to the power of m over im, and raise that expression to the power of im. So effectively, we've just left the expression the same, but we've just done some algebraic manipulation, inverting the im over m, and we've done the same thing to the index as well. So it can be shown that Euler's number, E, which is 2.718, and it's a non-terminating irrational number, can be found by evaluating the limit as x tends to infinity of 1 plus 1 over x to the power of x. So all that we've done with the right-hand side of our equation is we've just tried to make it look as close as possible to that expression 1 over x to the power of x plus 1. We take the limit of both sides is equal to the limit as m tends to infinity of 1 plus 1 over m over im to the power of m over im, and we raise that to the power of im. So as the limit as m tends to infinity, using the expression above for Euler's number, it is just e to the power of, and as m tends to infinity, we just substitute m for the infinity sign. So it's common to denote the continuously compounded rate of interest by r or by mu. And just substituting that into the equation, we have e to the continuously compounded rate of interest is just equivalent to 1 plus I, where I is the effective annual rate. Or again, by taking the natural logarithms of both sides of that equation, we have r is equal to the log of 1 plus I. Discount rates. A discount rate works somewhat inversely to a yield or interest rate. If an investor desired to invest a sum of money today, which would accumulate to a targeted amount at maturity, then the investor would need to invest the targeted amount minus a certain discount today. The amount of the discount would need to be such that at maturity the investment would grow to the targeted amount. If the investment yielded an effective interest rate for the period of I, the discount rate would be related to the final targeted amount by the following formula. Let D denote the discount rate, and let K be the targeted amount at the end of one period of investment. Then the relationship between the targeted amount and the amount invested today is given by K, 1 minus D, which is just us applying the discount to the targeted amount, and we accumulate that at the rate of interest for the period, 1 plus I, and at the end of the period, after applying the discount and accumulating at the rate of interest, all we'll have is K, the targeted amount, at the end of the period. We can simplify this expression to obtain D is equal to 1 minus 1 over 1 plus I. Let's illustrate this by means of an example. An investor buys a bond at a cost of 91 Rand or $91 today. The bond will not pay any interest during its tenor, but at maturity it would pay the investor 100 Rand or $100 at the end of 1 year. Calculate the implied discount rate on the bond and the equivalent annual yield earned by the investor. So the first part of the question asks us to calculate the implied discount rate. So we have a targeted amount of 100 paid at the end of 1 year. So the bond is sold at a discounted price of 91 Rand today. So if we apply a discount to the 100 Rand, we say 100 multiplied by 1 minus D, and that should give us the discounted price of 91 today. So solving that expression algebraically, we get a discount rate of 9%. To calculate the implied yield, we would use the formula D is equal to 1 minus 1 over 1 plus I, which after rearranging would give I is equal to 1 over 1 minus D minus 1. So we just substitute the value of D that we previously calculated, which is 9%, and we arrive at an interest rate, an equivalent interest rate of 9.89%. So we see that the discount rate and the interest rate are related. If we apply a discount at the beginning of a period of 9%, we would need to accumulate that new discounted amount by 9.89% in order to just arrive at the targeted amount at the end of that period. Discount rates are usually quoted as simple rates for investment products with maturities less than 1 year. If both I and D are simple rates, the relationship between the two is given by K, the targeted amount, multiplied by 1 minus ND, the percentage discount, and multiply that by 1 plus NI, the equivalent yield over the period. And then at the end of the period, you just get K back. So that would just equal to K. So N is the fraction of 1 full year that the investment is held for. In other words, if we're not talking about a full year period, N would just be the number of days between the two dates, the settlement date and the maturity date. And we divide that by 365 days or 366 days for a leap year, depending on the day count convention that we're using. So we can simplify that expression to yield D is equal to 1 over N multiplied by 1 minus 1 over 1 plus Ni. Or inversely, we could also solve for I to yield I is equal to 1 over N multiplied by 1 over 1 minus Nd minus 1. If D needed to be specified as a compound rate, then just as was the case for interest rates, we can use the following formula to convert between discount rates of different compounding frequencies. 1 minus dn over n to the power of n is equal to 1 minus dm over m to the power of m. Simplifying this gives dn is equal to n multiplied by 1 minus, and in brackets 1 minus dm over m to the power of m over n, and we close the big brackets and just multiply all of that by n. Finally, we can also convert from an interest rate at any compounding frequency to a discount rate of another compounding frequency. And that's given by the formula 1 minus dn over n to the power of n is equal to 1 plus im over m to the power of minus m. Simplifying this gives dn is equal to n multiplied by big brackets 1 minus, and in the small brackets 1 plus im over m, all raised to the power of negative m over n, and n would be multiplied by the big brackets. Or similarly, im is equal to m multiplied by big brackets, and then in smaller brackets 1 minus dn over n to the power of negative n over m, and then minus 1. Continuous compounding for discount rates. It can be shown mathematically that a continuously compounded discount rate is exactly equal to a continuously compounded interest rate. To see why this is true, recall that a discount rate expresses the amount of yield that is earned at the beginning of a compounding period, expressed as a discount to the maturity value, whilst an interest rate is the amount of yield earned at the end of a compounding period. For continuous compounding, we shrink the compounding period down to an infinitesimally small instant. Therefore, theoretically, the discount and the interest payments should occur at exactly the same time. Hence, the amount earned using a continuously compounded discount rate should equal the amount earned using a continuously compounded interest rate. In other words, E raised to the continuously compounded discount rate should be the same as E raised to the continuously compounded interest rate, and we just use mu to denote both of them. Taking the natural logarithms, we have minus the log of 1 minus d is equal to the log of 1 plus I, and which we just use the letter mu to denote the continuously compounded rate of interest of both expressions. In practice, discount rates are mainly used to price money market instruments and are usually quoted as simple rates for maturities less than 1 year. We will look at some of these instruments in the following section.